We present to you our project to reproduce the paper, Silent Trial Protocol, for the evaluation of real-time models at ICU. This project is done up by my teammate, Kento Otani, and I, Travistang. In this project, we reproduced a streaming data pipeline that uses deep learning to evaluate the risk of cardiac arrest with waveform data in real time. The streaming pipeline is orchestrated with Docker Compose. It performs the following in sequence. First, it creates streaming data of physiological signals from MIMIC III Dataset. It then sends the raw streaming data using Kafka, preprocesses the raw data using PySpark, predicts if the patient is at risk of cardiac arrest using PyTorch. It then stores the results in MySQL and displays the data and results in real time using Bokeh. Finally, in this project, we also compared the performance of the reproduced streaming data pipeline and machine learning model against those of the original paper. To get started, let me introduce you to the paper that we reproduced. The paper's main contribution is in a real-time data and machine learning model for cardiac arrest prediction. In particular, the authors collects the data from a bedside monitor of an ICU ward, processes streaming data with a streaming engine called Microsoft Trill, sends the data to a Python environment using a message queue called 0MQ, and eventually makes inference on these signals using PyTorch. Next, let's talk about the model used in the paper. The model predicts a cardiac arrest risk score that ranges from 0 to 1 for a patient every minute. To make a prediction, the model needs 10 simultaneous real-time signals of 10 minutes in duration. We will consider the paper to be reproducible if the data pipeline can achieve the following. First, a peak throughput of 3.9K input messages per second per signal stream. Second, a 50th percentile latency of 4.6 seconds and a 90th percentile latency of 64 seconds. And third, similar F1 scores as the paper. Next, we'll discuss how we built the data pipeline and the model. Here is the architecture of the streaming data pipeline that we implemented. First, we store the MIMIC III waveform dataset on our local. Using Docker Compose, we created multiple containers that can interact with one another. We first set up the containers for Kafka and Zookeeper. This is because we use Spark streaming, which enables the data to be streamed continuously, and it relies on Kafka and Zookeeper. Next, a container called SendStream is set up. It reads in the MIMIC III waveform dataset of one patient and sends the data to the next Kafka topic. The next container is called ProcessStream. It reads in the data from the Kafka topic and preprocesses the data and sends it to another Kafka topic. The next container, called Deep Learning, reads in the data from this topic and makes an inference using the PyTorch model. Note that to make an inference, the model needs not only the signals from the Kafka topic, but also the patient's age, which it reads from a MySQL table. The prediction made is then stored in another MySQL table. Finally, the container PlotStream is used to create a UI. Now that we have talked about the data pipeline, let's discuss how we built the model. To create the model, we first created the dataset by selecting 33 patients with known cardiac arrest timing and relevant waveform data from the MIMIC III waveform dataset. Then, we preprocess the data with low-pass filtering and interpolation. The preprocessed data is then transmitted to the ML environment. The deep learning model in the ML environment consists of two parts: a convolutional neural network to find the latent representation of the signal, and an LSTM network that captures the time dependency. Shown here is the architecture of the model. The model is trained with PyTorch with the following hyperparameters, and as seen in the training curve, the training and validation losses are declining in tandem, which shows that the model is learning well. Lastly, let's discuss how our pipeline and model performed compared to the authors. We showcase our result by first demonstrating the Bokeh user interface. The raw streaming data produced at a frequency of 1 data point per second is displayed on the bottom left charts. Note that even though we only displayed 3 signals here, there are actually 10 signals being processed simultaneously. The data is then pre-processed with the low-pass filtering and interpolation, which causes the waveforms to be smoothened out, as you can see on the bottom right charts. Lastly, the machine learning model uses the pre-processed streaming data as an input to make a risk score prediction every minute, as you can see on the top chart. Note that this user interface only displays one patient's data, even though the data of multiple patients are being processed simultaneously. We were able to reproduce the entire data pipeline, but its performance, in particular the latency and throughput, differed slightly from the paper's pipeline. Using 3 local threads, we obtained a latency of 6.5 seconds for the 50th percentile, which is longer than the authors, and a 6.7 second latency for the 90th percentile, which is shorter than the authors. Further, we obtained a peak throughput of 1.1k messages, but we are not able to meet the peak throughput performance of the author's pipeline, which is 3.9k messages. For the machine learning model, it performed decently on the test set, even though it did not perform as well on the paper's model. It did not perform as well as the paper's model. On the test set, our model achieved an AUC of 0.69, which indicates that it is performing relatively decently. But when comparing the F1 scores of 4 unseen test patients, our model performed poorer and had a larger variance than the author's model. The next slides will discuss why we think the paper cannot be precisely reproduced, how we resolve the challenges that we faced, and what we suggest the authors can do to improve the paper's reproducibility. Since they are self-explanatory, we will show them without reading them aloud. In conclusion, while the general architecture and approach of the paper is reproducible, the performances of the pipeline and the model are not so. That is the end of our presentation. Thank you very much.